Okay.
I thought I was important.
I know you are.
You don't hate it.
Okay. You are.
The hater.
Okay, so the standard model, by the way, Chris Murrayism deals with none of those problems, or none of that small feelings. I'm just trying to win you over to, okay. Here's the standard model, and this is the picture that people draw. Notice on the top is time, and pretty much all of the good stuff happened before 10 seconds, right? Something interesting happened at about 500,000 years. This is actually about 380,000 years. So you could correct that, cross off, instead of 500,000 years, make it about 380,000 years, cross that off there, okay? And then 10 to the 10th years, that's close to being 13.7 billion, isn't it? 380,000 years, yeah. Or 0.38 times 10 to the 6th years. Instead of 500, yeah. That's a small tweak, isn't it? Yeah. Okay. Notice also along the bottom side here that they're talking about temperature, and this is a weird thing. Isn't that a weird thing? Why are we talking about temperature and time? Well, what happens as time goes on? What's happening to our temperature? It's getting colder. This is about 3 kelvins, right? This is 3,000 kelvins. This is, yeah? Okay. Now, at 3,000 kelvins, it's hotter here. Okay. At 3,000 kelvins, there's actually a phase change. We go from plasma, so label this plasma, okay? This is just regular non-plasma. I don't know, what do you call it if it's not plasma? Gas, I don't know, right? It's, what's the difference? What is plasma, what's not plasma? What determines plasma? Electrons are stripped from the nucleus, correct? Don't electrons have to be, here, let's think about this. Doesn't plasma conduct electricity? Don't you have to have free electrons to conduct electricity? Yes. Okay, so plasma conducts electricity. It's therefore opaque. It's therefore opaque. Because all things that conduct electricity, electromagnetic waves have a real problem with it because they have an electric field. Electric fields can't exist inside a metal, correct? Or a conductor. So they basically, plasma short circuits the electric field of an electromagnetic wave. Okay, so in a plasma, photons bounce around, but they're just like little particles bouncing around in there. They're not like, you know, leaping off at the speed of light or something like that. They're just percolating around, and it's like a gas. Just picture, molecules in a gas. Yes? Okay. They're just bouncing off each other. There they go. The sun, the photons created by fusion in the core of the sun, take 10,000 years to percolate out to the exterior of the sun. 10,000 years. Yes? That's how long it takes light to get from the center of the sun to the outside, because the sun is all plasma, right? And then from the surface of the sun, they then can go out into free space. They travel the speed of light. They reach us in 8 minutes or something like that, right? Isn't that right? Okay. Now, as you look back, we're looking away from Earth and we look back in time. Notice that this is 10 billion years, right? Or 13.7 billion years more accurately. This is about 380,000 years. So almost all of the universe happened before this. This is a logarithmic scale, isn't it? Yes? Okay. As we look back in time, we can see through the universe, we can see through the universe. At some point, we can't see through the universe, can we? Isn't that right? So that's when we see the universe. When we say we see the big fiery wall, we're seeing it right at this point. So label this thing, put a little line on this thing, and label that. This is called the photon decoupling. Photon decoupling. Okay? So at this point, oops, I drew my little wedge of cheese too big, right? That little point right there, that is photon decoupling. And what that means is that the photons now are traveling in straight lines at the speed of light, right? When we see the universe, when we say we see those pictures of the Big Bang, that's what we're seeing. We're not seeing the moment of creation. We're seeing it when it suddenly let the photons run free. Up until now, they're all like just bubbling around like in the sun, a rate where it takes 10,000 years to percolate out of the sun, which is a pretty small object. After that, the photons are free. Okay? Now, understand that here is really hot, this is really cold. As you cool down, when we talk about cooling, we're really talking about photon energies. Now, here's a weird thing that photons can do. And we used to know this, but we don't know this anymore in IB physics, because it's not one of the things I'm supposed to teach you how to do, right? But this is one of the coolest things photons can do. If I've got a photon that's got enough energy. Let's say that it's got 1 million electron volts. Let's give it like 2 million electron volts or something like that, right? Okay, 1.2 million electron volts. This is like a photon. Like you know how they step out of the room when they give you an X-ray, right? Here you want to like step out of like the planet to give them an X-ray with these things, right? I mean, this is a disastrously energetic particle, right? This thing, if it passes near a massive object, can actually make matter out of its energy. But when you make matter, there's all these conservation laws, like conservation of charge, conservation of lepton number, all of these things that have to be conserved. So in this case, we have enough energy to make an electron and a positron. Okay, so I'm going to make an electron, and I'm going to make a positron, and these things fly off like this. Whatever energy is left over in making these is given to these guys in the form of kinetic energy, and off they fly. Yeah? What happened to the photon? The photon goes away and it creates matter and antimatter. This is called pair production, and it's fairly benign, fairly, this is not pie in the sky. This is fairly well observed phenomenons, right? Okay, so this is a positron. Notice that this guy's antimatter. This guy is matter. That's matter. This is antimatter. This is matter. All the laws, all conservation laws are obeyed because although this has a positive lepton number, this guy has a negative. Total number of leptons created, 0. Okay. This has positive charge. This has negative charge. Total amount of charge created, 0. Okay. Everything works. You've got to create equal matter and antimatter, and everything works, right? Now, there was a moment in the universe when basically the average energy of photons was 1.2 million electron volts. Holy cow, yes? But there was a time, wasn't there? Okay, so that means that at that time, electrons and positrons are created. Now what do they do? What do these electrons and positrons do? They wander around until they run into the opposite of them, and then they annihilate and create photons, right? And when they do that, when a positron and an electron meet each other coming through the Rye, they create a little explosion, and what emerges from them are 2 photons, 2.511 MeV photons, right? Only maybe a bit more if they had possessed kinetic energy when they collided, right? Okay, so this is what's going on in the early universe, is that you've got radiation, you've got this crazy mixture of radiation. You've got photons, you've got leptons, and in fact, back here in the hadron era, hadrons are things like protons, yes? Yeah. Protons are hadrons, okay? This is a crazy amount of energy. At this point, right, you're making hadrons, and hadrons are being created and they're being destroyed, okay? So it's making these things are running around annihilating these things, making photons. Photons are making matter. Matter is making photons. Are you picturing this? Yes, it's a crazy time to be alive, isn't it? Nothing was alive then. Okay, good. Okay, so there they are. They're making all these things. Now here's what's happening. Here's what's happening. It's sad. It's sad. But isn't the universe stretching out? Isn't the average photon energy going down? Yes, the temperature's going down. The average photon energy is going down, right? And as soon as you drop below a certain level, as soon as you drop below an average photon energy able to create hadrons, like protons and neutrons, don't you stop creating hadrons? You can't violate conservation of energy. You have to have the energy to do this, right? If you don't have the energy to do this, you can't create the matter. So aren't hadrons eventually going to quit being created? Right? Okay. So as soon as you stretch out enough, hadrons, and they talk about this like condensation. It's like distilling. When you distill stuff, you boil a mixture of stuff, right? And at certain temperatures, certain materials condense out. Well, this is what's going on here. At certain temperatures, hadrons condense out. Now, what happens? As soon as you can't make hadrons anymore, what happens? You've created equal parts matter and antimatter, so what's going to eventually happen? They're going to collide, and all the hadrons will be gone from the universe. Look around you. Look around you. Look around you. Do you see any hadrons around here? Yeah, I see a lot of stuff with protons in it. Yeah? So all this stuff we have, this is one of the questions, one of the more difficult questions, right? Is why is there stuff left? If we always created equal matter and antimatter, why, when it all cooled down, didn't the last hadron run into the last antihadron and annihilate and create energy that then stretched and was unable to make hadrons, right? Why is there stuff left? Well, the reason is well, we don't know.